cover this topic on AI-powered dynamic personalization today. So this is a joint work with a lot of amazing collaborators at TCS Research, including Diksha, Priyanka, Ankit, Dr. Lavkesh, and Dr. Gautam. So yeah, so I'll just get started. So this is an overview of what we are trying to do in the space of personalization and marketing intelligence. So I'll introduce each of these terms briefly here. So the goal of personalization and marketing intelligence is to um, enrich the experience of customers through dynamically engaging with them across various channels. So you can just imagine e-commerce platform while I go through any of this, right? And it will become easy to understand. Um, so on one side, you want to enrich the experience of customers by through dynamic engagement and showing them what uh, they really want at the right time through the right channel and so on. And then on the other hand, you have this business objective of maybe boosting sales, increasing revenue, or maximizing return on investments in case of any advertising campaigns and so on, right? So the whole goal of this work is to come up with the optimization algorithms and decision making agents that can balance these two seemingly contradictory objectives, right? So they might be contradictory in some cases, and in some cases they may not be. So the goal is to kind of balance this out and make sure that the experience of the customer is as good as possible, and at the same time you are able to boost some of your key performance indicators, right? So now one challenge in this broad towards this broad goal that we are focusing on is that often you do not have the luxury of just trying out things in the real world. So if I want to understand what this customer really wants, I can just show all the like one way to do it would be to show everything that I have with me one by one to the customer, and then arrive at a point where I know that okay, this is what this customer wants. And you can easily imagine that is not perhaps the best way of going about it, right? So you want to learn these agents, but uh, at the same time keeping in mind that uh, like you do this with as minimum number of trials or engagements with the customer as possible, so that there is minimal churn as well. So that is an additional uh, kind of aspect to this problem, right? So I'll be talking more about these things as we go along. And by the way, just feel free to interrupt me at any point in time. So I would like to keep this as interactive as possible. And so in other words, the research focus of this work is to learn decision-making agents for dynamic personalization and dynamic marketing intelligence. And so when I use these terms, personalization, marketing intelligence, so what you can just think of is some of the examples that are listed at the bottom here. So which products or items to recommend to a user, right, is a form of personalization exercise. And you want to dynamically adapt like what you want to show based on the real time context of the user. So that is the dynamic aspect of the problem. then whether you should make an offer to the customer or not. And if you decide that yes, making an offer might be useful at this point, then which offer or ad from a catalog of products, advertisements that you have, do you want to should be shown to the customer to like maximize some KPI. And then uh, how much budget to allocate to each channel, right? So you engage with customers across channels, and then these engagements cost. So for example, sending emails, sending push notifications, sending SMS, and so on, right? So which is the most effective budget for a customer at a particular point in time, right? So that is another aspect of dynamic marketing intelligence. So what I wanted to do today is to focus more on this dynamic personalization aspect. And within this, from the examples that are listed here, the first example, which is more of a recommender systems problem, which many of you might be familiar with, but a specific kind of recommendation systems problem that I'll introduce shortly. Right? So that is going to be the focus of rest of the talk. Now, before I dive into the technical details, so uh, a bit more detail on what all personalization encompasses, right? So you want to personalize for all kind of audiences, so or customers, right? So there are like different types of customers depending upon their demographics and so on, and even whether this customer has visited you earlier or not. So in other words, is the user or customer an anonymous user or a known user without for whom you know the historical transactions, you know the demographics. So you would treat these two kind of customers differently. And so you want to personalize at each stage in the journey of a customer on your platform. So whether the customer is at the browsing stage or trying to discover something, or once they buy something, then how do you want to engage with them? Or if they have removed something from their cart, then how do you want to engage with them? So that is the other aspect of personalization. Then on the other hand, so you want to personalize for every kind of entity through which you engage with the customer. So you engage with customers through showing different products, you engage with them through emails by sending them some personalized content, and you might give them offers either on your platform or through other channels like emails, SMS, social media, and so on, right? And then personalize based on the uh, real time context of the customer. So, what time is it? From which location the customer is engaging with you? What is the current things in the basket of the customer, or what is the history of this customer? Right. So, in the rest of the talk, I'll be focusing more on this part. So, intent-based real-time personalization, right? And yeah, as I mentioned, so there are like you want to personalize across different channels, and then each channel might have a different flavor to the personalization problem. Right? And these personalization problems are applicable across domains ranging from banking, insurance, retail, telecom, healthcare, travel, transport, hospitality, and so on. So, throughout this talk, I'll mostly take retail as an example, and because I think that would be most relatable to all of us. And yeah, so moving on, so going into a bit of technicalities of what I would like to discuss in the rest of the talk. So, This is about dynamic personalization and more specifically session-based recommendations. So, what I mean by session-based recommendations can be understood through this toy figure on top. So, let us say a customer visits your platform, let's say a website or a mobile app, and the customer has seen these three dresses. Then the role of the decision-making agent is to uh, create a list of uh, other dresses which the agent feel the customer would be interested in, right? So that is the goal here. So it's a recommendation problem. But the added point here is that you want to do this recommendation after each interaction the user has with the system. So let's say when the user had only seen one dress, what are the best recommendations you can give? Then when the user sees two dresses, then how would you like to adjust the recommendations? And three dresses, then so basically each interaction gives you some feedback, implicit feedback about the user, and you want to take into account while giving the next set of recommendations, right? So some definitions. So a session is a logical window of time during which a user is interacting with a platform. And the constraint that we are assuming here is that the user is an anonymous user. That is, the only thing that you have access to about the user is are the interactions the user is having on the platform within the current session, right? So this is also known as the user cold start problem. And then the goal is, given sequence of past interactions in the session, recommend relevant items a user might be interested in. Right? So now, if you are able to do this well, what are some of the like impacts that you can generate out of this? So one is you can maximize the clicks, or which can potentially lead to more buys. You will be able to adapt in near real time to each and every implicit feedback that the user is provided, either in the form of clicks or even skips, right? And then you are making recommendations based on how the customer's journey is evolving. So these are some of the kind of business related aspects of what you gain by building such a recommender system. Okay. And so what you are given, all this can be posed as a learning problem, wherein what you are given is a set of past sessions, and you have a catalog of items I, right? And then given a session S with of length small l with items I S1 S2 till ISL, right? And this then the goal is that given this session S, you want to rank the items in the catalog of in the set of items catalog I, such that an item with higher rank is more likely to be clicked next, right? So this is going to be the theme of the rest of the talk, like what we will be trying to solve. So um, moving on. So there are several ways to do this, and I'll focus on some of the approaches that we have considered over the last 2-3 years. So I'll start from the simplest of them and then try to go to the more sophisticated ones. And so these are based on heuristics, so things like k nearest neighbors, then representation learning, or you can say deep learning based approaches, and then deep reinforcement learning based approaches, and a recent approach viewing this problem from a causal perspective. So what I intend to do is to cover the heuristics and the deep learning or the representation learning based approach in some detail, and then just touch upon the deep RL and the causal approach. And we'll see how much time we have, and then we'll accordingly adjust. So yeah, so these are the approaches that we have proposed over the last 2 3 years. And so Stan, Nicer, BCD for Rec and Causer. So I'll be giving you at least a glimpse into each one of these. Won't be able to go into too much of technical details here. But yeah, so I'll get started with the first one, which is STAN, which stands for Sequence and Time Aware Neighborhood for Session-Based Recommendations. So this was presented at SIGIR 19. So, so as the name suggests, so this is a nearest neighbor based approach, but it uses few rules, or you can say thumb rules, which take into account the sequential nature of the problem and the temporal aspect of the problem. So what I mean by that is, so if you look at this toy figure on the left, so let's say there is an ongoing session of a user, say S, and what user has so far done is clicked on items I1, I4, I5, and I star. Now, after these interactions, the goal is to recommend the next list of items to this user. Now, so now one heuristic that we use is that uh, when deciding the relevance of other items in the catalog, more importance will be given to I star, then to I5, then to I4, then to I1. So the y-axis here shows the weightage that we can give to the different items the user has already clicked in the session to decide uh, the recommendation list. So it's fairly intuitive that so this is a very small example of 4 items, but imagine the user has seen 10, 15, 20 items. Then you can possibly reasonably assume that the more recent interactions of the items, uh, the more recent items that the user has interacted with are maybe more relevant, and then you want to show items which are similar to those rather than something which the user saw in the very beginning of the episode or the session, because the interest of the user or evolves as the user is exposed to more and more items, right? So this is the first aspect. The second one is also fairly straightforward. Uh, so let's say you are doing generating a recommendation list today. Then so you want to use the past sessions to generate this list. So now the further you go in past, the less relevant those sessions becomes, because trend is something which is very much there in the, especially the retail setting or even in entertainment setting. So you can assume either of these scenarios. So basically, when I am comparing the ongoing session with any historical session to see how similar these two sessions are, I'll keep in mind how old the historical session is. So if the session is very old, I don't want to give too much uh, attention to that session. So as you go into the past, the like weightage to the session decreases accordingly. Right? So, and then the third is that, let's say once you have identified a similar session to the current session. Okay, so here our current session is I1, I4, I5, I star, and then there is this session from the past, I2, I4, I star, I3, I9. So this is similar to the current session because there is an overlap of two items, I4 and I star, in these two sessions. Therefore, it is similar. And then what one can assume is that other items in this historical sessions would also be of interest to the current user, right? But then, how do you give weightage to the different items in this historical session? So there we again use the fact, uh, not the fact, we again assume that the most recent item that the user has interacted with, I star, let's say. So the items which are nearby to I star in these historical session would be of more interest to the user. So you'll give them a slightly higher weightage when computing the relevance of that item. Right. So these are the heuristics that we use. So this is fairly simple, nothing complex here. And looking at the same thing slightly mathematically, uh, I think I won't get into the details here, but essentially all these three rules or heuristics that I mentioned translate into some simple equations where we decide weightage of different items and sessions from the past, and then eventually generate a relevance score for each item for the ongoing session and generate a ranked list, right? So I won't get into the details of this. And then these are some results that we obtained, which were actually very surprising. So we were through this simple rules that I mentioned, we were able to kind of come very, very close or sometimes even beat the state of the art deep learning methods. So the take home lesson here is that sometimes simple things uh, are something that you may want to begin with rather than trying some of the more sophisticated deep learning things. So although this is a workshop on deep learning, but I think it is still very important to try out simple things first, right? So just to get a sense of what is going on. So just a bit of like details here. So uh, these four high level columns that you see, YC 1 by 64, 1 by 4 DNRR, these are different data sets from different domains. And then each row here is a different approach taken from literature and then compared to our approach, which is STAN. And then the metrics that we are using are recall at 20 and the mean reciprocal rank at 20. So, so the first kind of set of approaches here are more heuristics and neighborhood based approaches. So there, what we are showing is that by introducing this simple sequential and temporal information, you can significantly improve the performance. And what you see in the last four rows, so these are state of the art deep learning methods, and then you can see that we are fairly close to them through just these simple rules across all data sets, right? So this was fairly encouraging. And then on the right hand side, you see sensitivity of these three rules that I mentioned. So each one of them carries a certain sensitivity across data sets. So varying the parameters corresponding to each of these did have a significant enough impact on the performance, although different uh, each of these rules had a different level of significance, but all of them were somewhat critical to improving the performance, right? uh, uh, I'll take a pause here in case there are any questions, else I'll move to the next technique. Okay. Uh, so the next approach I wanted to discuss is a deep learning approach. So this is called NICER, which is normalized item and session representations for uh, session-based recommendations, while the focus here was handling popularity bias. So I'll explain what each of these terms mean. So the first thing to note here is that so this is again the same session based recommendation system setting. You are given past interactions in a session, and the goal is to predict the next item user is likely to click. So this can be posed as a n-way multi-class classification problem, where n is the number of items in the catalog. So basically, the input is the sequence of items the user has clicked, and then the output or your target label is what did the user click next, right? So when you are training, and then at inference time, you will be generating a probability score for each of the items in the catalog, and that will help you define the ranking of the items. So now this problem can also be seen through the, although it's a sequence of item interactions, it can also be seen as a graph. So let's say uh, because what is typically observed is that especially in settings retail, users typically go back to items that they saw earlier to kind of reconsider them or compare them with what they are currently looking at, and so on. So it results in something of the form of a graph. So I1, I2, I1, I3, I4. So it results in a graph like this. So basically, it's not just a flat sequence. There is a graphical aspect to this whole thing. Right. So then how can we leverage this aspect is one of the focuses of this work. And then the approach consists of like four high level steps. One is learning the representation of our items. So it is to be noted that we are like in settings like retail, so we are typically dealing with the uh, thousands or even hundreds of thousands of items, right? And then you want so if you just input each item in the form of a one hot vector, so it becomes fairly complex. So you look at representing these items in a lower dimensional space, and then similarly represent sessions in a lower dimensional space, and then try to compare the item representation and session representations to come up with the item session relevance score. So all this will become clear in the next few slides. So what you have here is, so you have this item representation matrix, or you can also call it as an item embedding matrix. So if you have m items, right, and each item is represented in a d-dimensional space, so you have this m by d dimensional matrix, capital I. And then for, let's say, the ongoing session I1, I2, I1, I3, I4, you uh, represent this in the form of a graph, and then where each node is an item, and then edges correspond to whether an item was clicked after an item or not, right? So that's how edges are defined. And then each node has a representation associated with it, which is simply taken from this item embedding matrix. And then we use a graph neural network to kind of update the representations for each of the items by informing each item about its neighbors. So for instance, the representation of I2 would be updated taking into account that I1 is a neighboring item for I2, and so on. So after passing through a graph neural network, you obtain updated item representations or updated representations for each node in this graph. And then you somehow uh, like consolidate all these updated item representations to come up with a summarized session level representation. So which is you can think of as a global representation of this graph. And we achieve this through attention network. So I'm not going into the details of like what a graph neural network is here and what attention network is, but I hope that you get the high level idea. So you get a session representation, and then you essentially compare this session representation with the item representation, and then the similarity kind of determines the relevance of each item for this session, right? And then you can do a softmax in case you are interested in probabilities and so on. So this is the high level idea. Now, one problem here with this kind of approach is related to this notion of popularity bias. So what this is that what has been seen in like most recommender systems setting is that so you typically have a very large number of items, but only a few of these items are actually popular and are recommended more often and therefore clicked more often, right? So what you see here is a typical distribution of popularity with respect to items. So it's a fairly long tailed distribution setting. So if we look at the original n-way classification problem that I mentioned, so it's a long-tailed classification setting, uh, and so there basically some of the target classes are very popular, and some and then there is a large number of target classes which have a fairly small representation in your data set. And then what we noticed is that this kind of an approach that I explained in the previous slide, which was at that point this state of the art approach, it depicted this kind of behavior, what I show on the right graph. So if I look at the performance in terms of recall of this approach, and I on the x-axis I have the popularity of the item. So what we see is that for the more popular items, the performance is very good. So it reaches something like zero point 0.7 recall and uh, of that order. Whereas for the less popular items, the recall was very bad. So of the order of zero point 0.1, zero point 0.2, or even lesser. Right? And then, interestingly, what you also see on the right y-axis here is the L2 norm of the item representations. So, as I said, that each item is being represented in a lower dimensional space, right? And so, therefore, it is a vector, and this vector has a norm. So we found a very strong correlation between recall and the norm of the item representations. Right? So basically, more popular the item is, higher is the L2 norm of its session of its representation, and also higher is its recall. So this was an observation, and then what this kind of implies is that so why this is happening is related to this inner product that we are doing in one of the last steps while computing the relevance of items, right? So I'll explain this in a bit more detail. So uh, basically what so there is this radial property of this softmax based loss function that if you just want to increase the probability score of a particular, let's say, item in our case, you can easily achieve that by just increasing the L2 norm of that item. So I'll again not go into the maths here. And so this has been shown in other computer vision settings uh, as well. So one simple way to basically address this popularity bias issue is to just replace wherever you have item representations, just restrict these representations to uh, have L2 norm of 1. In other words, just divide each item's representations by its L2 norm so that it becomes a vector of with unit norm. And by simply doing that, and you do the same thing for the session representation as well. So you convert S to S tilde, where S tilde is a unit norm vector, while the direction of S is retained. So this essentially means that the inner product is replaced with cosine similarity, and this leads to fairly significant improvements in the results, which are shown here. So if you look at like what the vanilla graph neural network based approach was doing versus what this normalized item and session representation does on these four data sets in terms of a metric which is used to measure the popularity bias of your recommender system. So we were doing fairly better there. And then the same is confirmed by the plots at the bottom, where on the x-axis you have increasing popularity, and on y-axis you have recall and MRR. So what you see is that these orange plots are significantly better than the blue plots for the less popular category of items. Right? So whereas it retains the performance on the high popularity items, and therefore it leads to overall improvement in the performance. And then a side effect of this is that you are able to show items which are relevant to the user but may not be very popular, and therefore significantly address the popularity bias issue. And this simple modification of normalizing of the item vectors and the session vectors leads to like state of the art results, as is shown here. And then ablation studies also show that the L2 norm was the most critical component in leading to these improvements. Right? So, and another implication of this handling of popularity bias is in the online learning setting, wherein new items are introduced over a period of time, and then during the initial few days those items have very small amount of data that you can use for training, because these items are newly introduced or newly launched. So you don't have a large amount of data that you can use to train the representations for these items and so on. So this is another flavor of like popularity bias, where newly introduced items are less popular during their initial phases. And what we saw was that even in this kind of a setting, this approach performs significantly better than the vanilla graph neural networks based approach. So yeah, so kind of take home message here is again that uh, like looking at the problem more from a practical perspective, in this particular case the popularity bias perspective, and then looking at various aspects where handling popularity bias can be useful, and then seeing perhaps what is the simplest way to uh, achieve that by looking at what exactly is going on in the state of the art approaches. So that was the kind of thought process in this work. So the contribution is fairly simple, but in my opinion, the uh, outcomes are significant. Right. So I'll take a pause in case there are any questions. I'll move to the next. Okay, so the next is a deep reinforcement learning based approach, and so I won't go into details of this in interest of time, but I'll still give you a sense of what are some of the practical challenges in using uh, deep reinforcement learning for this kind of session based recommender systems setting. Uh, So first of all, like what is the practical challenge that we kind of uh, consider here? So this is how a typical kind of pipeline would look like. So you would deploy an agent A. So when I say an agent, so it is a decision making agent. In our case, it is a recommender system. So you would obtain a recommender agent based on some simple things, like let's say the STAN kind of approach. So which is based on some simple heuristics or rules or domain knowledge. You would come up with a recommender agent that you would deploy, and you would collect data using that recommender system. Now, once you have collected a fairly large amount of data, next thing you want to do is that given this new data set, can I use this data to learn an improved agent? Right. So learning is the key here. So maybe you start with a heuristics based agent, but now once you have a large amount of data, you want to learn an improved agent, maybe through some deep learning based approach. And then if you are taking a deep learning based approach, so there is this problem of hyperparameter tuning, or like deciding which algorithm to use, what should be the depth of the neural network, how many, what should be the, let's say, the embedding dimension, and so on. So all these decisions have to be taken, right? Now, but you want to do all of this without actually deploying one of these learned agents in the real world and collecting feedback, because since these are deep learning based models, so they are kind of black box in nature, and you do not want to like simply go out and deploy something which you do not understand well. So what you want to do is to learn these agents in an offline manner, and then also possibly select the best agent in an offline manner, right? So things like making these decisions based on business rules or A/B testing, or even some kind of simulators, right? So it's kind of requires a lot of subject matter expertise, and this can be an expensive and time taking exercise. And so even just simply using this historical data blindly is likely to lead to failure, because the data has been collected from some uh, policy which is of course suboptimal. So you don't know what is the best way to use it to obtain an improved uh, policy or agent, right? So that is where our approach comes in. So just to put it in like a slightly different context, so you start with the suboptimal personalization agent, you deploy it in the real world, that agent interacts with the users, you end up collecting a lot of data, right? So things like for what kind of user, what was shown, and what was the response. Now, once you have collected this data, you want to learn an improved agent, and but the constraint here is that you are not allowed to again go out and interact with the users in the real world to obtain this improved agent. So that's the focus of this work. So why RL in this case? uh, so you can think of this as an interaction between a user and the agent, where the user becomes the environment and the recommender system becomes the RL agent that is interacting with the environment, collecting feedback, and then again taking some action, and so on. So the context or the state is the sequence of items that the user has seen so far, and uh, the the action from the agent is the list of items that the user is being shown, and then the response is whether the user clicks on any of these items or the user skips this list of items that the recommendation agent shows, and so on, right? So there is a state, an action, and the reward is in terms of what is the feedback from the user, whether the user clicks an item, buys it, or skips it, and so on, right? So the goal is to train a recommendation agent to obtain a policy pi that selects an action A, or where the action is a list or slate of items from a catalog of items I, given the current state S, such that some long-term expected reward, for example, the number of buys or clicks, is maximized. I'm sorry for all this noise outside, beyond my control. Uh, and so, as I mentioned, the constraint that we are posing here is that, so unlike the standard reinforcement learning setting, wherein the agent is allowed to interact with the environment in an like online fashion, so here we are just given some historical log data, and you still want to learn this reinforcement learning agent. So this is typically known as the batch reinforcement learning setting. And yeah, so this is what we looked at in this work. So in our context, so basically the agent is the recommender agent, and what the agent gets to know is the state or the session history of the user, then what the previous policy had shown to that user, and then what was the feedback or the reward. Excuse me. Right. So this is the setting here, and then so some of the challenges which are kind of specific to this recommender system setting, which is not there in some of the more mainstream reinforcement learning literature, is that the logs that you have a very poor coverage of all the possible state action pairs. So the state here is a sequence of item interactions. So that space is combinatorial in nature, right? So there is the item catalog itself is large, and then at each step, any of these items can appear. So the state space is pretty large, and then the action space, which again is of the order of the number of items in the catalog. So the action space is also pretty large. So of course, in the historical data, all the state action pairs cannot be covered. So this is one of the main challenges in this particular setting. Another critical challenge here is that there is inherent stochasticity in the user feedback. So, what I mean by that is, so here we are saying that the user is the environment, and the only access that you have about the user is what the user has clicked in the current session. Right? So it's a very partial kind of information that you have access to, and therefore how the user will respond to the next item that you show, that response is fairly stochastic in nature. So how do you take that into account? So in other words, each user is a different version of the environment. So whereas in typical RL, you just have one environment and the agent interacts in that environment. So here there is this additional complexity of each user being having different behavior due to all the latent aspects about the user that we have. And then, of course, the logs also have a popularity bias in them. So, in the sense that some of the state action pairs would be more popular in your logs compared to the others. So, these are the three things that we kind of went about addressing. So again, of very practical relevance. So the objective of this work was that, can this offline or batch reinforcement learning approaches improve upon suboptimal policies, which is your like the heuristic based recommender system from which you collected the data, given the large state and action space, and given the constraint that you are not allowed to, the RL agent is not allowed to interact with the environment in real time during the training stage. Right. So this was the objective, and so we were able to answer positively to this question. I think I'll skip all the details here in interest of time, but at a very high level. So some of the things that we focused on was that dealing with the large action spaces by using pre-trained action or item embeddings, then dealing with the lack of data for all state action pairs by uh, constraining what the agent is allowed, like the actions that the learned agent is allowed to take. So I know I'm being vague here. So there is something called as batch constraining that we relied on. And then for dealing with the uncertainty in feedback, which is a result of each user being a different version of the environment. So we dealt with that by uh, posing the RL problem in a distributional framework, wherein we are not only interested in the expected rewards, we are interested in the entire distribution of the future rewards when we are modeling the or the problem, right? So we use distributional RL to handle this notion of uncertainty, and then we also use this come up with a way to do offline model selection, which again is a critical aspect here, because till date I think it is not clear what is the best way to select RL agents in an offline setting. So that itself is a research problem. So we came up with some approach which worked fairly well for us, and then we tested in on two settings, one where we had a action space of around 7,000 items, and one another where we had a action space of around 200 items, and we compared with all the state of the art approaches. And then so one of the key takeaways here was that all these existing approaches, the supervised learning based approaches or heuristic based approaches, they struggle to improve upon the suboptimal policy from which you have obtained the data. And whereas our proposed approach BCD for REC was able to improve upon this behavior or the suboptimal policy across different metrics that were uh, considered. I'll skip the details here. And then we were also able to show that pre-training of these item or action embeddings was kind of critical to the overall performance of our approach. Through this distributional RL-based approach, we were also able to significantly handle the popularity bias issue, which I explained earlier is very prominent in recommender systems setting. And yeah, so we were also able to show that our approach does handle this notion of overestimation bias, which is the bias introduced by the poor coverage of the state action pairs in the historical logs. And yeah, so that's about this approach. And then I'll just touch upon the causal perspective. So how we looked at causality in the session-based recommendation settings. So we just looked at the whole data generation process of how the data is generated in session-based recommendation settings from a causal perspective. So basically, there is a session S and there is an item I which is recommended to a user, and then based on the relevance of the session of the item for the session, you have a particular outcome Y. So this is a simple kind of a causal graph of the problem. And then similarly during the training stage, which was the more critical aspect of like what we were looking at, um, so there is a session and then there is an outcome Y for when an item I is recommended for that session S. But what we show is that there are these confounding and mediating variables during the training stage, which are there as a result of the way stochastic gradient descent is used for training, say that GNN based neural networks. So I can get into the details of that here, but if you look at the whole training pipeline from a causal perspective, you see that there are confounding and mediating variables which should be taken into account when you are trying to estimate that for this session, when I show this item, what would be the outcome, right? So which is the whole focus of recommender system. You need to take into account these confounders and mediators, which was the focus of this work. And again, we were able to show significantly improved results compared to state of the art approaches through this causal perspective. And just to kind of closing remarks, we uh, uh, some of the next steps that we want to take. So these are like fairly sophisticated deep learning methods, but one of the asks from the business is you want explainability around these learned agents. So how can we do that? And what does it even mean in this context of recommender system? That is something we are looking at. And then handling this notion of non-stationarity of concept drift, because the behavior of users evolves over time, the market conditions change over time. Pandemic is a classic example of like how customers behaved before pandemic and then during pandemic on these e-commerce platforms. There was drastic changes there. So how do you deal with that? And then how do you use simulators to simulate some of, like, so let's say if you decide that I will give 10% discount on this item in this geography over the next 1 month, so you want to see what is the potential effect of this going to be. So can you build some simulators or digital twins for doing that, right? So these are some of the things that we are looking at right now. Yeah, so I think I'll stop here, and thank you for patiently listening to this.
Thank you very much,
Thank you.
Pankaj sir, for the very intuitive and very interesting presentation. Actually, the very good thing about your presentation is that we are made aware of the ongoing efforts in the industry side so that we can also orient our research. I think the researchers, the faculties, and other people among the participants, we can orient our research according to the needs of the industry and the current time. Thank you so much for because in the last lectures, I think we have discussed a lot about different models, and now you have summarized the different models and how they can be. I mean, they are getting into use. So that is really interesting for me, and I hope our participants it would have been a great learning experience. Now we'll take up a couple of questions, sir. So participants, if you have any questions, please. Drop in the chat box, or you can also raise your hand and ask the question. Yeah, Dr. Sangeeta Chaudhary. Sangeeta ma'am has raised hand. Can you
Yeah,
unmute? Yeah,
yeah. Good
okay.
morning, sir. I have as you mentioned, recommender system and all AI-based system. So I just have one question or curiosity. Like nowadays, we are, as you said, some of the research issues is like explainability and all. So related to this thing, like if we are taking this as a very genuine problem to be solved, so how it will be seen from the perspective of responsible AI?
Mhm. Right. So I think the whole notion of explainability and even so the thing I touched upon, popularity bias, right? So these are, I think, sub problems within the whole responsible AI space. So this can be viewed from that perspective. And then So most of the settings that I spoke about were in a kind of a two stakeholder setting, so that there is this platform which is building this recommender agent, and then you have these customers that you are interacting with. But if you look at these aggregator platforms like Amazon's or Flipkart, right? So there is this third stakeholder, which is the different vendors, right, or different brands that are different suppliers on these platforms. So I think in those contexts, responsible AI. So like, how do you balance the interests of the users, balance the interest of these suppliers, vendors, and then also balance your interest, right? So so their responsible AI becomes very critical. And then I think some of our work on handling popularity bias would have applications in that setting. And then looking at the larger picture, so like kind of drawing a causal diagram of what exactly is going on, what is affecting what is affecting what, right? So that kind of puts down all the assumptions, or like the real scenario out there, and then you can actually build algorithms using that. So I think that is my current take on how we can go towards responsible AI, building upon some of the things that we have done. Of course, there might be other approaches, but yeah, those are my thoughts at this point.
Yeah, thank you, sir.
So
Thank you,
there is a
sir.
question from
Yeah. Okay, go ahead,
Yogesh.
sir, please.
Yeah, for image classification, mostly CNN is used. Do we have any scope in GNN for image classification? So I am not pretty sure, but I think so. People have used GNNs for not the like the standard image classification, but if you bring in other notions, like if you start looking at videos, or you look at graph over like different objects of interest, then I think there is literature on graph neural networks for image classification. Maybe not for the like traditional ImageNet kind of classification, but maybe more uh, recent and challenging formulations of image classification.
Thank you very much.